Hello guys, welcome back to your favorite and India's most affordable learning platform, Physics Wala. So in the last session of gravitation, we discussed about the gravitational field concept and gravitational potential concept and what's the relation between the gravitational field and the gravitational potential, right? So in continuation of the chapter gravitation, so where we are going to deal with the lecture number 4 today. So in lecture number 4, our main objectives are the gravitational potential energy and the interesting topic, that is escape velocity. So these are our two main objectives for today's session. So as usual guys, I just need your attention for the next 1 hour. Just be with me, avoid all the disturbances around you, and at the end of the lecture, it's very important to prepare your own short notes. Okay, chalo. So without wasting much time, let's get into the topic. So the first one, so what is gravitational potential energy, sir? So the gravitational potential energy, it occurs due to the configuration of system. So what does it mean by configuration of system, sir? Let's suppose any two masses, if they are placed at some distance r1, now you have to change the configuration. That means, so you have to bring them closer or move them apart like this. So the initial distance is r1, so now the configuration is changed to some other distance r2. So then the initially when these two are placed like this, so the potential energy stored in them will be, so the u initial we can say, so the potential energy here u initial, this is a u initial, the potential energy initial. So and then here when the configuration is changed, so the potential energy stored will be the u final. So always the potential energy difference exists. The potential energy is not going to exist, the potential energy difference will exist. So what is the potential energy difference now? So the delta u, so the delta u is equals to, so the potential energy final minus the potential energy initial. So initial potential final minus initial is a change in potential energy which is always exist. Okay, so this change in potential energy is equals to, so the work done by the conservative force, negative of the work done by the conservative force. Did you guys remember this from the work energy power chapter? Yes. So the change in potential energy is equals to, so the negative of the work done by the conservative force. And one more thing, so here, so the change in potential energy, I can write it as, so here which force we are talking about when we are changing the configuration of these two masses. So then the conservative force, that is the gravitational force between them, this is the gravitational force. Yes or no? Clear? Chal. So now this change in potential energy delta u is equals to, so it's a negative of the work done by the gravitational force. It's a negative of the work done by the gravitational force. Always remember this one guys. And then, so we have also studied that, so the work done by the conservative force, the negative of the work done by the conservative force will be equals to the work done by the external agent. Did you guys remember that from the work energy power chapter? We also studied that, so the work done by the negative of the work done by the conservative force, the negative of the work done by the conservative force is equals to, so the work done by the external agent is the work done by the external agent. Yes. So now here I can substitute this one here in place of work done by the negative of the work done by the conservative force, or which is the gravitational force. In place of this I can write the work done by the external agent. So the change in potential energy is equals to, so it's a work done by either external agent or negative of the work done by the conservative force. So any of these you can use. Okay, so understood the concept. So the potential energy, the gravitational potential energy develops, so whenever there is a configuration change from original configuration to some other configuration, if you are changing, so then the change in gravitational potential energy, which is the delta u, so the change in gravitational potential energy it is. Okay, done. Chal. So now, so the gravitational potential energy of a system of two particles, see here, m1 and m2, which are at a distance r. So it's the amount of work done by an external agent, so in bringing each mass from infinity to the present configuration. So from where to where? So let's suppose initially we consider at infinity there are two masses. At infinity there are two masses at some configuration. That means configuration means they are at some distance. Now you are bringing them to some other configuration, like, so the distance between them is r. Okay, so now, so whatever the work done you are doing, so from here to here, so whatever the work that you are doing, that's called the potential energy. So here I can write without any change in its kinetic energy. See, let me tell you simply. So the change in potential energy is equals to, so the U final minus U initial, U final minus U initial. So here, so U final, let it be, and then U initial, this is 0. The initially they are at infinity, you are bringing them, so each mass from infinity to the present configuration. So they are at infinity distance now, so you are bringing them to the present some configuration. So the potential at infinity is considered as 0. So the assumption, always remember, so the potential at infinity is considered as a 0. So U at infinity is 0. So that, so this part will become 0. So from here, so the U final, so which is nothing but, so the potential energy formula, so which is minus G m1 m2 by the distance between them is r. So this is a potential energy. It is not at a point, so it is actually the difference only. So but initially it is 0. Initially it is 0 because at infinity the potential energy is considered as 0. Understood this part? Clear, guys? Chal. So done. Yes, next. So now the gravitational potential energy of a system of particles, if there are three masses like this or some more masses, so then we can write r12, so let it be r23, the distance between these two, and this is r13, let it be, so the distance between these two. So now let me write, so the net potential energy will be equals to, between these two masses the potential energy will develop 1 2, between 1 2, and between 2 3 the potential energy will develop, and then between 1 3 the potential energy will develop. That's it. So now between 1 and 2, so what's the potential energy? G. So the masses are m1 m2, so the distance between them is r12 minus, so between 2 and 3, so the masses are m2 m3 by, so the distance between them is r23 minus, so between 1 and 3, so the masses are 1 3 by, so r13. Yes, done. So this is the potential energy due to the system of particles, the gravitational potential energy for a system of particles. Sir, if there are three particles like this, we can simply decide. But if there are n number of particles, so how many potential energies we have to add? So that's called number of configurations. So for the number of configurations, you can remember this formula, guys. The number of configurations, for the number of configurations, it should be n into n minus 1 by 2. So I'll tell with the question so that you will understand better. See, for this one there are three masses, right? So how many potential energies we have to add? That means between how many systems this potential energy will exist. Okay, so here n we substitute 3. So if you substitute 3 in this particular question, 3 into 3 minus 1 by 2, so which is 3 into 2 by 2. So 2 gets cancelled. Here 3 into 2 by 2. So 2 gets cancelled, which is 3. So that means 3 potential energies will develop. So the net, which will be equals to between 1 2, between 2 3, between 1 3. So this is the number of configurations. Okay, now clear, guys? Chalo. So let's see the next one. So in this particular question, we have to find the gravitational potential energy of the system. So total how many masses are there? 4 masses are there. So let's find number of configurations first. First, let's find the number of configurations. How many configurations exist? Number of configurations, which will be equals to n into n minus 1 by 2. So here how many masses are there? N is 4. 4 into 4 minus 1 by 2. So which is 4 into 3 by 2. So 2 ones are 2 twos are. So 2 into 3, 6. So that means the gravitational potential energy will be due to 6 configurations. Due to 6 configurations. What are those 6 configurations, sir? See here. So if you consider them as 1, 2, 3, 4. Right? So the potential energy between 1, 2, then 2, 3, then 3, 4, then 1, 4, then 1, 3, and then 2, 4. That's it. Done? Understood? So simply you remember this formula. If there are 5 masses, you can simply substitute 5 into 5 minus 1 by 2. Okay. So if there are 6 masses, 6 into 6 minus 1 by 2. That's it. Okay. So let's do this question now. Now, so I can write. So the net potential energy will be between 1, 2, between 2, 3, between 3, 4, and between 1, 4, and between 1, 3, between 2, 4. Yes or no? Shall I write like this? So 1, 2, 2, 3, 3, 4, 1, 4, 1, 3, 2, 4. So that's what I wrote. So now, so you know the distances also. So all these distances are, it is of the square form A. So now only the distance that changes here, it is this one. So this distance, what it will be, and then this distance also A root 2, right? So this distance will be A root 2 and this distance also will be A root 2. So you can simply substitute now. So the first one, all the masses are m only, right? So I can simply write minus gmm by A. Next one also minus gmm by A. Next one also minus gmm by A. Next one also minus gmm by A. And the next one minus gmm by A root 2. And then minus gmm by A root 2. Yes. Simple one. Right? Chalo. So these 4 I can add. So which is minus 4g mm. So mm means m square. Minus 4g m square by A. So these 2 I can add. So minus 2g m square by A root 2. Yes. So now, so options, how the options are, minus g m square by A, you can take it out. So minus g m square by A. So if you take it out, so here g m square by A minus also common. So 4 left minus. So here what it is left, g m square by A minus also came out plus. So 2 by root 2. 2 by root 2. So is there any option like this? See here, minus gm square. So you can just 4 plus 1 by root 2. No. Minus gm square by A. So let's take the LCM. So minus gm square by A into, so root 2 is the LCM. So this will be 4 root 2 plus, so 2. So what we can do is, so take 2 common in the numerator. So let me write it here. So let's do the simple maths here. So minus gm square by A. So you can take 2 out in the numerator. So if you take 2 out, so it will be 2 root 2 plus 1 by root 2. Right? So I can cancel 1 root 2 here. So minus gm square by A. So root 2 will be left here into 2 root 2 plus 1, because I am writing this 2 as root 2 into root 2. So 1 root 2 gets cancelled, 1 more root 2 will be left. So again you can send it inside if needed. So minus gm square by A, so which is, so 2 into root 2 is 2, 4 plus this is root 2. So which is the correct option is minus gm square by A, 4 plus root 2, right? 4 plus root 2, 4 plus root 2 minus gm square by a, 4 plus root 2. Option 2 is the correct one. Done? Understood this part? Simple calculations, that's it. Do the calculations properly, that's it. Chalo. So let's move further, guys. So what's the amount of work done on the system if the mass m at C is taken to infinity? Okay, see here. So initially there are 3 masses like this. Okay, then C mass m is taken to some infinity. So at infinity the potential energy is considered to be 0, guys. So if you take this to some infinity point, so the potential at infinity is considered as 0. So first let's divide this question into 2 parts. So one is initial configuration. So and then the next one is the final configuration. So initially 3 masses are there, m mass, and m mass. So these are at a distances a, and a, right? So the total potential energy will be equals to, so the net potential energy initial, so I can write initial is equals to, so minus gm square by a minus 3gm square by a. I am directly writing, okay, because between these two gmm by minus gmm by a, between these two minus gmm by a, between these two minus gmm by a, so total minus 3gm square by a. Fine. So now finally this mass has taken to infinity, so that only a mass will be left here, a and b. So these two only will be left. This is a, this is b, because this mass has taken to infinity. Okay, so the final potential energy will be equals to, so I can write like, so what's the formula? Minus gm square by a, minus gm square by a. So then what we need actually? We need, so the amount of work done. So what's the amount of work done? So the work done by an external agent will be equals to, so the change in potential energy, right? So the work done by an external agent. So to take this mass from here to here, you need an external agent, right? The work done by the external agent will be equals to the change in potential energy, which is minus u final minus u initial. What is u final? Minus gm square by a, u final minus u initial minus 3gm square by a. Yes, so from here, so which is minus gm square by a plus here it is 3gm square by a, 3gm square by a. So here 3 minus 1, which is 2. So the final answer will be 2gm square by a, guys. So 2gm square by a. Option 2 is the correct one. Done? Simple question. Just you have to understand the concepts. That's it. Okay. Chal. So let's move further. So the gravitational potential energy of an object due to earth. Let's suppose, so there is a mass m is placed on the surface of the earth. So consider the radius of the earth be r. So the earth has some mass m. Okay. So then, so the potential energy, the gravitational potential energy between these two, so will be given as minus g mass of the earth, and small m is the mass of the object, by, so the distance r. So minus gmm by r, minus gmm by r. So where the potential at infinity is actually, so this mass is not at the surface initially. So what we do actually, so we bring it from infinity. We bring it from some infinity to earth. So final minus initial we write. So finally the initial is 0, final minus initial. So the potential at infinity is 0. The assumption is the potential at infinity is 0. Always the change in potential energy exists, guys. Remember. So if you are writing at the surface of the earth, means this mass is not initially existing here. You are bringing it from some infinity point. Okay, so you are bringing it from some infinity point, so where the potential at infinity is 0. So generally we write like this: delta U is equals to U final minus U initial. Okay, so that U initial is nothing but U infinity, which is 0. You are bringing it from infinity, so it is 0. So the change in potential energy will be equals to U final. U final means when you brought it to the surface of the earth. So then that is minus gmm by the distance is r. That's it. Understood? So when the object is very near to the surface of the earth, this is the formula, guys. This is the potential energy when any object which is near to the surface of the earth. So the gravitational potential energy by the earth is this much. Done? Clear? Chal. So let's move further. So now, what is the change in gravitational potential energy when an object is taken from surface of the earth to some height h? See, initially the object is at surface of the earth, okay, and then finally it has taken to some height h. Okay, so this is the radius of the earth r. When it has taken to some height h, so the total height will become, this total height will become, shall I write h plus r? H plus r. So when it is on the surface of the earth, we know the potential energy. So the U initial is equals to minus g mass of the earth and mass of the object. The distance between those two is r. This is the initial potential energy. Yes. Now, so what's the final potential energy? So the U final, which will be equals to, so when it has taken to some height h from the surface of the earth, so then the total height will become, you have to calculate the height from the center of the earth, guys, always. Okay, so minus g, again the mass of the earth and mass of the object. Now the distance between these two, so the distance between center to center you should take always. So which is r plus h I am writing. This one r plus h I am writing. Okay, so chalo. So we need the change in gravitational potential energy. What is change in gravitational potential energy? So U final minus U initial. Okay, chalo. So U final, what is U final? Minus gmm by, so r plus h minus U initial. So minus of gmm by r. That's it. Yes. So this is the change in potential energy. Now I can write here. So the change in potential energy delta U is equals to, so minus gmm by r plus h. So this is minus of minus, it will become plus. So plus gmm by r, right? So let's do one thing. So delta U, so let's take gmm out, gmm. So take it out. So I'm writing 1 by r minus 1 by r plus h. So I'm just writing the reverse, 1 by r. This part is minus, right? So I'm writing minus 1 by r plus h. So chalo. So the delta U is equals to gmm. Sorry, this is capital M is the mass of the earth. See here, I'll write here. So capital M is the mass of the earth and small m is the mass of the object. Small m is the mass of the object. Small m is the mass of the object. So gmm into, so r into r plus h, right? So take the LCM here, r into r plus h. So that here r plus h will come minus, so here r plus h is there, r will come. So r gets cancelled. So the delta U is equals to gmm into h by r into r plus h. R into r plus h. Okay, clear this part, everyone? Done? Chalo. So now let's move further. So I'll write the change in potential energy. Write the same thing here. So gmm h by r into r plus h. R into r plus h. Okay, so this is what we got, right? Gmm by gmm into r. Gmm into h by r plus r into r plus h. Yes, fine. So now let's do one thing. So the small concept. So that is, let's divide everything by r, so that we get, so or else in place of this g you can write this one. So we know that the small g is equals to gm by r square. The small g is equals to gm by r square. So from here, so the gm, capital Gm is equals to g r square we can write. The capital Gm is equals to small g into r square we can write, just cross multiply. So then you substitute this in place of this gm. Okay, so just write it aside like this. So then we substitute this here. So the delta u is equals to, in place of this gm, g into m, I am writing g r square, small g r square into m into h by, so what is left, r into r plus h, r into r plus h. So here r gets cancelled. So we left with, so the gravitational potential energy, so the delta u is equals to what's left here, so m into g into h into 1r is left by r plus h. So let's do one thing, let's divide the numerator and denominator by r, so that I'll get, so delta u is equals to mgh, I am dividing it by r, mgh, and then here also r, if we divide, so 1 plus h by r, it will be, divide each term by r, so that the final we get it as 1 plus h by r. Yes, so this is called the change in potential energy when an object is taken from surface of the earth to some height h. So we generally think that, so the potential energy, so which will be equals to u is equals to mgh. So the u is equals to mgh is not always true. Okay, so this is true when, so I'll write the condition. So if h is far less than the r, if we have taken the object from the surface of the earth, so to some height where that height is negligible when compared with the radius r, radius of the earth. Okay, so if h is far less than r, so this value almost tends to 0. If h is far less than r, so h can be considered almost 0. So if h is 0, 1 plus 0 by something, 0. So then delta u will become, I can write mgh. So because this is 0, 1 plus 0, 1. So mgh by 1 is mgh. That's it. So this is valid only when the height is far less than the r. Okay, clear? Understood, guys? So this is what you should remember. So this is a derivation part actually. So you can just remember this part. So the change in potential energy when the object is taken from surface of the earth to some height h. Okay, so where that height h is comparably equal or greater than the radius of the earth. Okay, chalo. So remember this formula again. I'm writing here. So the delta u is equals to mgh. You can remember it always. So plus 1 by h by r. So where h is a, to what height you are taking the object from the surface of the earth. So we'll solve the question so that you will understand better way. So take this question, guys. So what's the question says here? Take the question. The work done to raise a mass m from the surface of the earth to a height h which is equals to the radius of the earth. So here, see here. So initially, so you can write like this. Initially, the object is on the surface of the earth. Okay. So then you are taking the object to some height h. So where this height h is equals to the radius of the earth. Initially, this is the radius of the earth, and you have taken it from surface to the height h, where h is equals to r. Now, what is the work done? So the work done is equals to change in potential energy. The work done is equals to the change in potential energy. Yes. So now, so what is the change in potential energy here? So don't take simply mgh, because the height is comparable to the radius of the earth. So then in such cases, so you can take mgh by 1 plus h by r, right? So therefore, so I can write, so the work done, therefore, so the work done is equals to, so we can write mgh by 1 plus, in place of height, h is equals to r here. So the h is equals to r. In place of h, we can simply substitute r. So that this is going to be 1. So that work done is equals to, we can write mgh by 1 plus 1, 2. So mgh by 2. So it's a mgh by 2. So what is h? H is equals to r, right? So let's do one thing. So in place of h, you can substitute r. So mg in place of h, r by 2. So here we get mg r by 2. So half mgr, option 1 is the correct answer. Done? Clear guys? Chalo, good. Let's move for the next question. So what's the question says? Read the question. So read the question first. A body of mass m is taken from the earth's surface to the height equal to twice the radius of the earth. Twice the radius of the earth this time. So then the change in potential energy of the body. Same concept you can write directly. So here. Chalo. So initially the object is on the surface of the earth. So radius r. So then it is taken to some height h, where the object is taken to this height where h is equals to twice the radius of the earth. So in this case, the change in potential energy delta U, so it will be equals to mgh by 1 plus h by r. 1 plus h by r. So now substitute the values guys. mg in place of h, I am writing 2r. In place of h, you can write 2r by, so 1 plus, in place of h, you can write 2r by r. So here r gets cancelled, so that we left with the delta U is equals to, so 2 mgr in the numerator by, so it is 1 plus 2, which is 3. So the delta U is equals to 2 by 3 times mgr. So 2 by 3 times mgr. 2 by 3 times mgr. Option 2 is the correct one guys. Done? Clear? Chalo. Fine. Let's go for the next one. So the next question. So what's the question says? A body of mass m is placed on the earth's surface. It is taken from the earth's surface to a height h is equals to 3r. So the change in gravitational potential energy, same thing again. So here height, okay, fine. So initially it is on the surface of the earth. So the radius of the earth is r. Now it is taken to some height, so where the h is equals to 3r. So the h is equals to 3r. So they are asking directly the change in gravitational potential energy. In the question they may frame that what is the work done or what is the change in potential energy. The work done will be equals to the change in potential energy guys. Okay, chalo. So let's do it. So the delta U is equals to, we have got mgh by 1 plus h by r. 1 plus h by r. So that mg in place of h, let's write 3r by, so 1 plus h is 3r by r. R gets cancelled. So it is 3 mgr in the numerator by, so here it is 1 plus 3, which is 4. So therefore 3 by 4 mgr. 3 by 4 mgr. So which is option 1 is a correct one. Okay, done guys. Clear? Chal. Simple questions. Directly the formula based questions, these are all. Chalo. So let's move further. Assuming that the gravitational potential energy of an object at infinity is 0. Yes. So the change in potential energy, final minus initial, of an object of mass m when taken to a height h from the surface of the earth is given by, see here. So we know the direct formula as mgh by 1 plus h by r when it is taken from the surface of the earth to some height h. But here it is given in terms of capital M and small m. So see here, and r plus h terms are also there. See, let's write whatever the formula that you know. So what's the formula that we know? So the delta U, the change in potential energy, is mgh by 1 plus h by r. So but actually you need it in G, capital G and capital M. So what we do is, so the small g is equals to gm by r square. The small g is equals to gm by r square. So let's substitute that here. Let me write. So m into, so h here 1 plus h by r, 1 plus h by r into, so in place of this one, so we can write in place of g, so I can write gm by r square. In place of this, so we can write gm by r square in place of small g. So now, so in the numerator, so we have got g m m h by, so here you can take r as the LCM, so that here it will be r plus h into, so here r square, so here r square, r gets cancelled, so that we left with, so the g m m h by, so r into r plus h, g m m h by r into r plus h, g m m h by r into r plus h. Okay, so this we already got it in the derivation somewhere here. So where is that? So this we already got it here. So where is that? Where is that? Where is it? G m m h by r into r plus h. So from here we changed this gm to, in place of this gm we wrote small g into r square. Okay, now clear guys? Done? Chalo. Good. Next. So now the next, so that is the conservation of mechanical energy. So if an object is taken from one place to another place, so you can apply the conservation of mechanical energy there, right? So what's the conservation of mechanical energy says? So if there is no energy loss, if there is no energy loss, so the energy can transform from one form to the another form. That's what the conservation of mechanical energy says, right? So the initial kinetic energy plus, so initial potential energy is equals to, so final kinetic energy plus the final potential energy. Yes guys, so this is a concept we are going to apply for the next questions and next concepts. So just you can remember this. We'll go for the questions. Chalo. So let's go for the next question. See here, what's the question says? First read the question guys. An object is dropped from h is equals to 2r on the surface of the earth. Find the speed with which it will collide with the ground by neglecting effect of air. So there is no air resistance. We can use the conservation of mechanical energy. So first see, understand the concept here. So here this is the earth. So now an object is dropped. Here the object is dropped, so from some height h. So from how much height? H is equals to 2r. H is equals to 2r. So when this hits the ground, this mass, so it will collide with some velocity v, right? So let's apply the conservation of mechanical energy between these two now. So the conservation of mechanical energy we can apply here. So which is nothing but, so minus g, let's write initial potential energy plus initial kinetic energy is equals to final potential energy plus final kinetic energy. Okay, so what is the initial potential energy? So when it is placed at a distance h is equals to 2r, so the initial potential energy between these two masses will be minus gmm by 3r. Let's write it in capital Gm because the options are in capital Gm. Okay, so then, so plus this one, it is k initial. So initially it is dropped. So whose initial velocity is 0? So initial kinetic energy 0. Done. So final potential energy, so it comes to the surface of the earth. So which is nothing but minus gm by r, right? So final kinetic energy half mv square. So done. Now do the calculations. So bring this to this side. So we can get this as minus gmm by 3r plus gm by r. So which is equals to half mv square. Yes. So from here, so the 3r is the LCM. Done. Chala. So this goes minus gmm and then this one, so 3gmm. So which is half mv square, right? So now do the simple calculations here. So we can write this as, so 2gmm by 3r is equals to half mv square. So small m gets cancelled. So we can write, so this v square is equals to, so 4gm by 3r. So I have sent this 2 to this side, 2 into 2, 4. So then here v will be equals to, so square root of 4gm by 3r. So 4 you can take it out, so which is 2. So 2 into root over gm by 3r is the correct answer. So check the options now. So where is the options? Here only, right? So 2 into root over 2 is not there. So 2 into root over 3gm by 3r. Yes, second is the correct. So no. Done? Clear, guys? Chal. So let's go for the next question. So what's the question says? Read the question first. So with what velocity should a particle be projected so that its height becomes equal to the radius of the earth? Okay, so its height should become radius of the earth. So with what velocity a particle should be projected? First, let's suppose this is the surface of the earth. The object is on the surface of the earth initially. Now it is thrown with some velocity u so that it reaches to a height where this h is equals to r. Yes. So then its final velocity when it reaches to some height, it becomes 0, maximum height. So there is no air resistance. I can take the conservation of mechanical energy. So the conservation of mechanical energy we can apply here. So what's the conservation of mechanical energy says? So the initial kinetic energy plus initial potential energy is equals to final kinetic energy plus final potential energy. So initially, so it is thrown with some velocity u, so that half mu square is the initial kinetic energy, and initially it is on the surface of the earth, right? So it is at the radius r, so minus gmm by the radius r. So the final kinetic energy 0, and then final potential energy it is reached to, so minus gmm by, so it reached to a height of, so h is equals to r. So this r distance and this r, total 2r, that's it. So from here I can write this part as, so we can write this as, so half mu square minus gmm by r is equals to minus gmm by 2r, right? So small m you can cancel everywhere. Chalo. So then I can write this, send this to that side, half u square is equals to minus gm by 2r, so plus gm by 2r, sorry, gm by r. Send it to that side. We need u, right? So what is the, so with what velocity? Yes, we need u. So half u square is equals to, so 2r is a LCM, it will be minus gm, this will be plus 2gm. Done. So half u square is equals to, so 2gm minus gm by 2r. So 2 gets cancelled. U square is equals to this much. U is equals to root over gm by r. So u is equals to root over gm by r, which we can also write it as gm by r whole to the power 1 by 2. So gm by r whole to the power 1 by 2. So the option 1 is the correct one. Clear? Done, guys? Understood? Chal. So let's go for the next question. So now let's go for the next concept, that is escape velocity. See, what is escape velocity, sir? So for the earth, so it's a minimum velocity with which you can throw an object so that it escapes the gravitational field of the earth. Okay, so it should escape the gravitational field of the earth. So with what velocity you should throw an object so that it escapes the gravitational field. If it escapes the gravitational field, so it will not come back to the earth surface. So it will move away from the earth. Okay, done? Chala. So that's what. So the minimum velocity with which a body must be projected vertically upwards so that it escapes the gravitational field of the earth. Okay, now. Chala. So it escapes the gravitational field means very far distance. So let's suppose it is reaching some infinity point I am taking. So that at infinity the kinetic energy considered to be 0. So the potential energy also considered to be 0 at infinity. Yes, chal. So then let me apply. So the conservation of mechanical energy from initial position to the final position. So let's apply the conservation of, so the conservation of mechanical energy. So the U initial plus kinetic energy initial is equals to, so U final plus the kinetic energy final, right? So initially it is on the surface of the earth, so that the potential energy possessed by it will be, so minus gm, so mass of the object is small m by the radius of the earth. And then, so what's the initial kinetic energy? So it is thrown with, let's suppose, some velocity ve, so that, so we can write half m ve square, half m ve square, which is equals to, so u final 0, u initial k final 0, because you are throwing it to some far distance. Okay, so at infinity in physics the far distance is nothing but infinity. Okay, so at infinity the potential energy is taken to be 0 and kinetic energy is taken to be 0. So that's it. So now let's do the calculations. What we can write here, so half m ve square is equals to, send this to this side, gmm by r, gmm by r. So the small m, capital M gets cancelled, so that the ve square is equals to 2gm by r, or else we can also write the escape velocity is equals to root over 2gm by r. So the escape velocity formula is root over 2gm by r. Okay, so let me write it in the next page. So the escape velocity is equals to root over 2gm by r, where here the g is the, capital G is the universal gravitational constant, universal gravitational constant. Okay, and then, so whose value we know that 6.67 into 10 to the power minus 11, right? Chal. So and then capital M is the mass of the earth, capital M is the mass of the earth, so whose value is 6 into 10 to the power 24 kg. Okay, actually it is 5.98 into 10 to the power 24 kg, so you can take it as 6 into 10 to the power 24 kg approximately. And then the radius of the earth, which is 6,400 kilometers, or you can write it as 6.4 into 10 to the power 6. So this is the radius of the earth, so which is 6.4 into 10 to the power 6 meters. Okay, done. So if we substitute all these values, so this escape velocity, because all are constants, 2 value, g value, m value, r value. So if you substitute all these values, so that escape velocity comes out to be somewhere around 11.2 kilometer per second. So that means if you throw an object from the surface of the earth at a velocity of 11.2 kilometer per second, so per second it should travel 11.2 kilometers. So then it escapes from the gravitational field of the earth and it reaches to the space. Okay, this is the formula behind the rockets actually. So if a rocket has to escape the gravitational field of the earth, because the rocket has also some mass, right? So it will be attracted towards some center of the earth. Yes, so if it is not thrown, if it is not given an initial velocity of 11.2 kilometer per second, it will not escape from the gravitational field of the earth. Done? Chalo. And one more thing guys here. So you can also write this formula in terms of small g. How? So we know that the small g is equals to gm by r square, right? So from here, so the small gm is equals to gr square we can write. So now let's write the escape velocity formula. So that escape velocity is equals to root over 2gm by r square. So 2gm by r. So here root over, in place of this gm I am writing, so gr square, g r square by r. So which is nothing but r gets cancelled. So this is root 2 g r. So in terms of small g, so the escape velocity is this much. Here also you can substitute the values. So the small g value you know, the radius of the earth you know, and 2 is the constant. If you substitute and do the square root for that, you will get the same value. So 11.2 kilometer per second. Done guys, understood? So this derivation, you should remember the formula here. Everyone should remember the formula here. So if an object is thrown with a velocity 11.2 kilometer per second from the surface of the earth, so then it escapes from the gravitational field of the earth, and the velocity that which we are throwing it is called the escape velocity. So for the earth it is 11.2 kilometer per second. Hope it is clear. Done. Good. Chalo, so let's take the simple questions. So one by one. So it's better I can stand this side or that side. You can read the question. A particle of small mass m is thrown upwards from the surface of the earth with a velocity u. So the mass and the radius of the earth are respectively capital M and capital R. G is the gravitational constant and small g is the acceleration due to gravity on the surface of the earth. So the minimum velocity of the u, so that the particle does not return back to earth. The particle does not return back to earth. So that means you should throw it with the escape velocity. So that u is nothing but the escape velocity, right? So which is equals to either root over 2 gm by r or else so root 2 gr. So the formula is given in which terms? See here. So in terms of capital G and see here. Root 2 gm by r square? No. Root 2 gm by r? Yes. Root small g m by r square? No. Root small g r square? No. Option 2 is the correct one. Direct formula based. Yes or no? So this question is directly the formula based. Done? Chalo. So the escape velocity of the sphere of mass m is given by, so g is the universal gravitational constant, me is the mass of the earth, and re is the radius of the earth. So they are asking escape velocity formula. So either you can write root over 2g mass of the earth by radius of the earth, or else you can write root over 2 small g radius of the earth. Any formula you can write. So which is there? So root 2 g m e m m, no. So root 2 g m e by r e, yes. M e 2 missing, sorry, here 2 missing. So option 2 is the correct one. Done? Everyone. Chal, good. Chalo, so let's move further guys. Next question. The escape velocity of a body on the surface of the earth is 11.2 kilometers per second. So if the earth's mass increases twice its present value and the radius of the earth becomes half, the escape velocity becomes. So here one thing that you should write here. So first thing is the escape velocity formula VE is equals to root over 2 gm by r. So where the mass of the earth is m and radius of the earth is r. So now what is the new escape velocity if this value is 11.2 kilometer per second? Fine. So what if, so the radius of the earth becomes twice, so radius becomes half and mass becomes twice. Let the new escape velocity VE dash, so where, so which is root over 2g into mass, let it be m dash, and radius let it be r dash. So in the question they gave that, so the mass becomes double, right, twice. So that m dash is equals to 2m and the radius, new radius r dash is equals to half the radius of the earth. So substitute these values here. Root over 2g. So what is m dash? 2m by. So what is r dash? R by 2. Right? Chalo. So then, so here I can write, so 2 to 4. So in the numerator 2 into 2 4. So 4 you can take it out, root. So here again this 2 will go up, root 2 gm by r. So already we know this. This is the escape velocity of the earth, 2 into VE. This is the escape velocity of the earth. So how much it is? 2 into. So this value is already given in the question, 11.2 kilometer per second. So which is nothing but 22.4. The new escape velocity will be 22.4 kilometer per second. So the new escape velocity is 22.4 kilometer per second. Done? Understood? Chalo. So let's go for the next question. For a planet having mass equal to the mass of the Earth, but radius is 1/4 of the radius of the Earth, so then the escape velocity for this planet will be. So here, let's remember this. Let's do this part. So the escape velocity is equals to root over 2gm by r, where mass of the Earth is m and radius of the Earth is r. So this value we know it as 11.2 kilometer per second. Yes. So now, so they are saying for a planet, so there is some other planet, whose mass m dash is equal to the mass of the Earth. Fine. But its radius is r dash, let it be its radius r dash, whose radius is 1/4 of the radius of the Earth. So r by 4. So then what is the escape velocity? So the new escape velocity ve dash is which is equals to root over 2gm dash by r dash. That's it. So we can write root over 2g value is constant, and then m dash. So what is m dash? Mass is same. So m, and radius r dash. So I am writing r by 4. So this 4 will go up and comes out. So 2 root over, so 2gm by r again, because this 4 will go up, and then 4 if you take it out of the root, so it comes as 2. So 2 into, so this is nothing but escape velocity again ve. So which is 2 into 11.2. So which is nothing but again 22.4 kilometer per second is the correct answer. Again the correct answer will be 22.4 kilometer per second. Done? Understood guys, everyone? Chal. So let's move further. So some important points related to the escape velocity. So just read them. The escape velocity does not depend on the angle of projection. It does not depend on the angle of projection, guys. So it does not depend on the angle of projection from the Earth surface. Okay, but as the Earth rotates about its axis, right, so that it becomes easier to attain escape velocity if the body is projected in the direction in which the Earth is moving. So in the direction which the Earth is moving, in that direction if you throw, so you can attain the escape velocity easily. Okay, but it not depend on the angle of projection, guys. So you can throw with vertically upward, or you can throw with some inclined angle. So your wish. Okay, so it will not depend on the angle of projection. And as the escape velocity depends on the mass and radius of the planet, yes, so the escape velocity formula is what? V is equals to root over 2gm by r. So it's depending on the mass of the Earth and radius of the Earth. So for different planets, different mass will be there and different radius will be there. Yes, so that's why the escape velocity is different for different planets. So for all the planets, the escape velocity is not going to be same. For different planets, it will be different. So if you want, you can see the next third statement. A planet will have atmosphere if the root mean square velocity of its atmospheric molecules is less than the escape velocity for the given planet. So this we'll see it in the 𝐄𝐍, kinetic theory of gases. So that's why the moon has no atmosphere. Moon has no atmosphere. So whose escape velocity is simply 2.3 km per second. If you throw an object with 2.3 km per second on the moon, so you can easily escape from its gravitational field. While the Jupiter has a thick atmosphere. The Jupiter has very high atmosphere. So thick, dense atmosphere. So its escape velocity is 60 km per second. Per 1 second, you have to throw it with a 60 kilometers distance. Imagine, on the Earth it is 11.2 kilometers. On the Jupiter it is almost 6 times that of the Earth, the escape velocity. Understanding? Chalo. So even the lightest hydrogen cannot escape from its surface. From the Jupiter, even the lightest particle, so the hydrogen cannot escape. Okay, you can simply remember these points. Okay, so the very important point is, so the escape velocity is not same for all the planets. The first point. And the second thing, the escape velocity, it will not depend on the angle of projection. For different, you can throw with any angle of projection. Okay, but it should reach the velocity, that's it, 11.2 kilometer per second, that's it. And you can remember that, so if the atmosphere is very, very dense, so then we can say that the escape velocity also will be more. So for the Jupiter, which has a very dense atmosphere, so its escape velocity is almost 60 kilometer per second, whereas so the moon has almost no atmosphere, so that its escape velocity is 2.3 kilometer per second only, whereas Earth has atmosphere, so its escape velocity is 11.2 kilometer per second. Done? Clear? Sure. Good. So now, if the Earth has to become the black hole, the escape speed must become equal or more than the speed of the light. So first, what is black hole, sir? So tell me, what is black hole? Anyone? So what is black hole? So the black hole is nothing but, so where even the light can't escape from it. Even the light can't escape. So it is very dense. So the black hole is so very, very, very dense. Okay. So if the Earth has to become very, 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 very dense, that means black hole, even the light should not escape from the Earth, so that if, when it is possible, so the escape velocity, if it is greater or equals to c, the greater or equals to c, so which is nothing but root over 2gm by r must be greater than or equals to c, or else we can also say that, so the root 2gr must be greater than or equals to c. Done? Clear, guys? Yes. Good. Next, let's move further. So take this 13th question. So what's the question says? The escape velocity from the Earth is 11.2 kilometer per second. If the body is projected in a direction making an angle 45 degrees, they said Earth. So angle of projection 45 degrees to the vertical. So then the escape velocity. See, the escape velocity does not depend on the angle of projection. So the escape velocity, it doesn't depend on, it does not depend on angle of projection. It does not depend on the angle of projection. So that's why I can say that, so whether you throw it the 45 degrees angle, 60 degrees angle, or 30 degrees angle, or 50 degrees angle, so the escape velocity remains same, 11.2 kilometer per second only. Okay, chal. So next question. For a satellite, escape velocity is 11 kilometer per second. So if the satellite is launched at an angle of 60 degrees with a vertical, so the escape velocity will be same thing, 11 kilometer per hour only. Okay, so the escape velocity, same answer. Again, you can write the same. The escape velocity does not depend on the angle of projection. Done? Yes. So let's take the next question. The ratio of escape velocity to that of the escape velocity of the planet whose radius and mean density are twice that of the Earth. See, so here we have two things. One is the Earth, so the other one is some planet. So this is Earth. So the Earth has, let's suppose, the mass m and radius r. Okay, so and then its density rho. Okay, and then so there is some other planet whose density is twice that of the Earth. So its density is 2 rho, and then whose mass is mass we can't say. So here whose radius is twice. Okay, first let's write the escape velocity formula in terms of density. So first let's write here. So the escape velocity of Earth. So the escape velocity of Earth in terms of density. In terms of density. So let's write that. So we have got, so the escape velocity formula is equals to root over 2gm by r. So the escape velocity VE is equals to root over 2gm by r. So now Earth is considered as a solid sphere. So this is the Earth whose mass is m and then radius is r. So this Earth is considered as a solid sphere, right? So this Earth will have the density rho, let's suppose. So the density of the solid sphere is nothing but mass upon volume from here. So the mass is equals to the density into volume. Yes. So the density into, so I can write what is the volume of the solid sphere, 4 by 3 pi r cube, basic maths, right? So in place of mass, so now I can substitute it here. So the escape velocity is equals to root over 2 into g into, in place of mass I am writing 2 into 4 by 3 pi r cube whole by r. Okay, so fine. So the escape velocity is equals to, so here 1r gets cancelled, r square will be left in the numerator. So and then 4 into 2, 2 into 4, 8. So root 8 g rho pi r square by 3. Or else if you want, you can take r out. So you can take r out. So which is r into square root of 8g rho pi by 3. So this is the escape velocity in terms of density. The escape velocity in terms of density. So now see here, let's see this question now. So what we can write? So the Earth has, so mass m and density rho, and the some other planet, this is the some other planet whose mass, whose radius is, let it be r dash, which is twice the radius, and whose density rho dash, which is twice the density of the Earth. So we know that the escape velocity of the Earth is r into root over 8g rho pi r. R is not there. 8g rho pi, 8g rho pi, 8g rho pi by 3. Yes, sorry. 8g rho pi by 3. So now, so the escape velocity of the planet will be, let it be VE dash. So which is equals to, so the radius of the planet r dash into, so root of, so 8 is constant, g is constant, and rho, let it be rho dash, pi is constant and 3 is also constant. So I can write VE dash is equals to r dash. So in place of r dash you can write 2r into, so root over 8g. So what is 8g rho dash, which is 2 rho pi by, so 3 I can write. Chal, so good. So then the VE dash is equals to, so I can write this as 2r. So let it be, so then, so 2 into 8g rho pi by 3. Okay, so or else you can take better. So the VE dash is equals to 2. So here root 2 you can take it out, root 2 into r into, so root over 8g rho pi by 3. Simple calculations. Okay, so in place of this one I can substitute the escape velocity of the Earth. So the VE dash is equals to 2 root 2 into the escape velocity of the Earth. So now what we required actually, so what is the ratio of escape velocity of the Earth to that of the escape velocity of the planet? So Earth to planet we required. So Earth to planet, VE by VE dash. So if you send it this side, so send this to this side, 1 by 2 root 2. So which is nothing but 1 is to 2 root 2. That's it. So which is nothing but 1 is to 2 root 2. Option 4 is the correct one, guys. Done? Everyone clear with this? Chalo, good. So this one you can just write it as a concept. So let me put it above this question. Better. Yeah. So now it will be better. Now the next question. So what's the question says? So a black hole is an object whose gravitational field is so strong that even light cannot escape from it. So to what approximate radius would Earth have to be compressed to become a black hole? So if Earth has to become a black hole, what should be the radius of the Earth? See here. So what's a black hole condition? If the Earth has to become the black hole, so the escape velocity should be greater than or equals to the c. The escape velocity should be greater than or equals to c. Just now we discussed. So the escape velocity should be greater than or equals to c. So now the same thing I am substituting here. So which is nothing but root over 2gm by r should be greater than or equals to c. Then so here 2gm by r should be greater than or equals to c square, squaring it on either side. So now 2 into, so g value 6.67 into 10 to the power minus 11. Yes. So already they gave it in the question, huh? No. So we know that value. And mass of the earth they gave, so 5.98 into 10 to the power 24. So I am taking it as approximately 6 into 10 to the power 24 by, so 2gm by r. What is r? R is the radius of the earth, which is 6.4 into 10 to the power 6. Right. So here 6.4, 6.67 almost cancel. And then here, so greater than or equals to c square. Sorry, don't cancel this one because we need the radius, right? My bad. So this is 6.67. So this radius, how much it should be, they are asking. So then, so this c value you can substitute here. So don't write c. So substitute. So c is 3 into 10 to the power 8, right? So I can write 3 into 10 to the power 8, 3 into 10 to the power 8. So 10 to the power 16. So 9 into 10 to the power 16. C square means, right? Chal. So then the r will be equals to, so the r will be less than or equals to, send this to this side. So we can write 2 into 6.67 into 10 to the power minus 11 into 6 into 10 to the power 24 by, so 3 into 3, 9 into 10 to the power 16. So now do the calculations, guys. So what's the r less than or equals to? So do the simple calculations. So 2, this is almost 2 3s are 3 2s are 3 3s are, right? So 3 1s are, so 3 2s are, and 3 2s are, and 3 2s are 2.22, something like that. So this will become r less than 4.844, something like that, into, so we left with 10 to the power minus 11. This is 10 to the power 24 into, this is 10 to the power minus 16, right? So then this comes out to be r less than or equals to, so 10 to the power minus, this is 27 minus 27, and then this is going to be 10 to the power 24, which is 10 to the power minus 3, 10 to the power minus 3. So 4 into 4.44. So approximately the r should be less than 10 to the power minus 3. So I can take approximately. So what is the closest value? You can check it in the options. So 10 to the power minus 2. Yes, I can put this. So that means if earth shrinks its radius to 10 to the power minus 2 meter, what is the radius of the earth now? 6,400 kilometers, or 6.4 into 10 to the power 6. So if the radius of the earth shrinks to 10 to the power minus 2 meters, then earth will become the black hole. Clear? Understood, guys? Chalo, this is the standard result you can remember. So instead of doing these calculations, actually this is a standard result. Done? Clear? Chalo. So that's it from my end for today's session, guys. So this is all about the escape velocity and the gravitational potential energy. So in the next class, we are going to discuss the motion of the satellite. Okay. So till then, keep studying. All the very best. Bye. Take care, guys.